Thank you for inviting me here. So this is a joint paper with Wei Bin and Hao Zhou. Let me start with the motivation. So as is well known, the standard risk-based models have trouble to explain many asset pricing puzzles. Here are at least some best-known examples. First one, the equity premium puzzle. So the equity premium implied by the standard model is too high compared to the data, too low compared to data. The risk-free rate, but it's too high, compared to data. And also, equity premium is time varying, it's very volatile. So these are the puzzles, the standard models have trouble to explain. This is another puzzle people don't pay much attention to. I call this the variance premium puzzle. So by definition, the variance premium is the difference between the expected stock market variance under the risk-neutral measure and under the objective measure. At least two stylized facts about the variance premium. The first one is that the average variance premium is too high. If you have a standard model, the variance premium is close to zero. But in the data, it's about 10.8% in percentage squared, monthly basis. Okay, that's the first puzzle. The second one is that the variance premium is very volatile. Okay, it's time varying and also forecasts equity premium. Let me show you the data. This is monthly data from January 1990 to the recent years. And you can see here the variance premium is very volatile, especially in recessions. This recent recession, you can see, is very volatile, and also on average, the size is bigger. Here is the recession here and here. But the interesting thing is that you can see here, it's also very volatile, and also on average is large. It seems that there was no recession here. What happened to here? And this is, I think this is related to the Asian financial crisis. Okay, so it's also very volatile here. And here, look at this figure. This figure illustrates that the variance premium is procyclical. It's countercyclical, I'm sorry. This GDP data and then this variance premium is standardized. Okay, that's the data. So we want to depart from the rational expectations. We'll make a distinction between risk and ambiguity. So we can motivate this here in two ways. One, there's a large literature on experimental evidence. There's Auersperg paradox and many other experimental studies. The second motivation is related to Hansen-Sargent work. The model misspecification, the model uncertainty. You want to have robust decision making. And it turns out this distinction is meaningful, behaviorally meaningful, and also it is useful. It helps us understand many asset pricing puzzles and also even business cycles. Martin has a recent paper on this topic. So the goal of this paper is to provide an ambiguity-based model to explain the variance premium puzzle. So that's the goal of the paper. All right, so let me talk about the related literature. So this is literature, this is also large literature on variance premium, this is empirical literature. So I only cited my co-author here to confirm, he's very good at this variance premium stuff, This is one of the early literature on this topic. And then there's some theoretical models, like risk-based models. Drachsler and Yaron have a paper to explain the variance premium puzzle based on the risk-based models. You need several features to explain this. You need a long-run risk, Of course, you need absent utility. And also, that's not enough. My co-author actually has an early paper to show that with the Tolkien also has a paper about this. These two elements are not enough. You need volatility in volatility to make it work. And also you need maybe jumps, because variance premium in the variance, that's high moments, you need volatility, in volatility. So, and there's also a recent paper by Drachsler. He I think he's the first paper based on the ambiguity version to explain this puzzle, his model is also pretty complicated. He has also many elements there, I think he also has jumps, many other things, to explain variance premium. So our paper complements his study, we have some features in the model that he does not have, but our model is much simpler. So we want to propose a parsimonious model. Okay, it's a very simple model. There's no jump here. No volatility, whatever. But it's a jump in the drift, not in the volatility there. And also, well, we have learning, but his model does not have learning there. Okay. The model also is quite successful, but we have still a long way to go. It's not a perfect model, I would say. But our model can match variance premium reasonably well, and also we can match equity premium, risk-free rate, and equity volatility simultaneously. Okay. Before I present the model, let me briefly review the literature of models of ambiguity aversion. Okay. So the earliest, best-known model is the max minimum model, expected utility model, also called the multiple priors model, proposed by Gilbert and Schmeidler in 1989. So this the model is very simple, and it's intuitive. So suppose the decision maker is unsure about the true model or the belief. You don't have you have uncertainty. And then you have a set of priors. For each distribution, in the set of priors, you compute expected utility, and you choose the worst case. You take the minimum. And then the Epstein and the Wang generalize this model to dynamics to make it work. In finance, in macro. They generalize this model to dynamic. So that's the model here in the first line. So yes, set up the model recursively. That's the current utility, and then your continuation utility. You take the minimum. So this is the set of beliefs. It's one step ahead. Okay. However, this model has a gap. In the sense that this is one step ahead. You want to think about whether you have a set of priors over the full space, a full state space, and this gap is closed by Martin here. Schneider, Epstein, Schneider. And then, you have, this is a full state space distribution there. And you can update the distribution. And also, you have to make it time consistent. So that's the model. And then this is the model widely used in the literature. And then Chen and Epstein also propose continuous time models. Okay? So let's see what we can do about this model. So whenever you introduce a new utility model, you have some actual degree of freedom. For this model, the degree of freedom is this is P, the set of priors. You can play around. You can specify the set of priors in whatever way you want, to match data or to explain something, And there are some interesting features of this model in applications. For example, you can have potential kinks, and you can have inertia. Like Philip presented a paper here. And also first order, equity premium is first order, and you can do first order approximations, These are nice features, for people to apply, And also, if you want to do more complicated model in macro, for tractability, typically you can guess what's the solution, The solution will be at the corner, I can guess, whenever you can solve, It should be in the corner, Otherwise, you have trouble to solve it. And then, this raises the issue of observational equivalence. I can start with the model with the expected utility. You have pessimistic behavior, and that's your belief. I can write on the model. It's going to be the same as your solution you have. And then people may say, why do you do this? Do ambiguity aversion, And you can give an answer, say, okay, I have a better micro foundation, You can provide a micro-founded interpretation of distorted belief with expected utility. Okay? And the other issue is that, it's a multi-prior model, you can say, what is ambiguity? And what is ambiguity attitude, you may ask. Similar to risk, you have risk and risk aversion, that's two different concepts, they're different things. But however, for the multiple priors model, these two things are mixed together, There's no meaningful ambiguity aversion there. So people don't ask this question typically in the seminar, but you can ask, so what is risk ambiguity aversion? What's the degree of ambiguity aversion? So which is different from degree of ambiguity or confidence level, whatever. And then this raises the question of a calibration of estimation of P, the saddle price, or one step ahead distribution, whatever. It's similar to risk and risk aversion. Risk, first order degree of stochastic dominance, second order degree stochastic dominance. And risk aversion, you have a parameter for the degree of risk aversion. That's your attitude. But we may ask whether there is a similar notion in ambiguity aversion models. So that's the question. I think this also partly motivates the researchers, and also there are many theories here. They want to deviate from this model. Otherwise, we stop here. There's no progress in terms of research. And actually, this ambiguity aversion literature is one of the most active areas in decision theory. And motivate this motivation, you want to have some new models. You want to deviate from this model. And here, I just list some models here, not all the models. So this model, I believe, they have more applications in finance or in macro. The second model, I want to say, this is variation utility. This is the utility. You take the minimum, but here you have this cost, like this motivated by robustness. You can have a distorted model, distortion here, and this is a cost, the penalty here, and you take the worst case. It's also intuitive, and also all these models, the special case of all these models is the multiple price model. So you include the multiple price model as a special case, but you want to deviate more, you have more, actual flexibility to work on. The one special model is also multiplier model. It's also very tractable for people to use, and you specialize this entropy, this cost function by the entropy criteria here, okay? And also this similar issue here is observation equivalence, it's also there, And some models are equivalent to expected utility, recursive utility or absent utility. But also the response, I think, is similar. Okay, it's fine. I have no problem with that. Because it gives you better foundation, better interpretation. You can still apply. But another nice feature is that it's smooth. So ambiguity version, is not. Kink is not necessary for ambiguity version. You could have smoothness, but it still have ambiguity version. And the smoothness is useful, sometimes it's tractable. As long as you don't want to explain like inertia, kink, or whatever, you can use smooth model to explain some phenomena. Okay? And also nice feature here is that for this type model, beliefs are always endogenous in the sense that the worst case beliefs will respond to the data, And also, it's not specified or estimated exogenously, This is solved in the model, state dependent. Okay, that's a nice feature here, I think, And the final feature is, whenever you work on this, apply to finance, that's a countercyclical pricing kernel. That's a very interesting feature, very useful feature to explain asset pricing puzzle. I'm going to show you later. Okay, and also the question whether you can work on this dynamics, and also they propose dynamic model. And you may ask whether this is a continuous time model, and actually there is a continuous time model. And we can work on, I have some note, and also some people, Hansen also, Sargent have a paper on this, And then the last model I want to mention here is this smooth ambiguity model. So that's the model here. It's also very intuitive form, The inside of here is like expected utility. And then you have a set of priors, Whenever you have ambiguity version, typically you have a set of priors there, That's the pi, But you don't take the minimum. And you have another, you're averse to that. And then, similar to risk aversion, you introduce a prior over there, and you apply another, concave utility function there. So that's the intuitive interpretation for this model, okay? So the U describes risk attitude, and the V describes ambiguity attitude, okay? And the pi is a set of probability measures. And the mu is the subjective prior, okay? And this model has a separation between ambiguity and ambiguity attitude, and also separation between ambiguity aversion and risk aversion. Okay. All right, and this is a dynamic model proposed also by KMM This is the current utility, and this is continuation utility. You just embed the static model in the dynamic model. And there's a learning here. So suppose Z is a hidden state, unknown parameter, for example. And this is the likelihood, the conditional likelihood. And the mu t is the posterior, okay? And you have a concave function, between these two expectation operators, okay? So this is non-Bayesian, this is irreducibility of compound lotteries, okay? However, this model has a limitation in the sense that there is no separation of ES, elasticity of intertemporal substitution. And we have learned from Epstein Zing, that this separation is important, okay? So, and of course, this model also has this feature, countercyclical pricing kernel, which is useful for asset pricing now. And this leads to my work, So that's why I want to have this model here. So there's a separation between, EAS and the risk version and ambiguity version here, okay? So that's the functional form, we have this axiomatic foundation for this model, and this is the application here. This W is the aggregator. It's similar to Epstein Zing model. And RT, that's the, I call this uncertainty aggregator. This is the continuation utility VT plus 1. And this comes from the static KMM, model. Here, this is, in dynamics, this is the likelihood, and this is the posterior, all right? And in applications, you need to specify functional form. So we specify functional form, in this way. It's also inspired by Epstein Zing, this homothetic form. So this is the CS aggregator, and this is power utility, and this is power. Okay, this is homogeneous. And this is related to also Mukherjee paper. They don't have how much homogeneity. Yeah. And then there's three parameters we can separate. This one is the EIS, risk aversion. The EIS, this risk aversion, and this ambiguity aversion. If eta is bigger than gamma, you're ambiguity averse. Otherwise, ambiguity loving. If they are equal, that's the Epstein Zing utility. And you can reduce, these two expectation operator. This is the identity function, and you can reduce this distribution together. That's the Epstein Zing utility. Okay, it's a special case. Of course, multiply is also a special case. If you drive, this ambiguity version to infinity, you're going to get this minimum here. That's also Epstein 1 and Epstein Schneider model, multiply model. Okay. And this is another issue, always have trouble, people always give me a hard time here, Oh, you have a degree of freedom, But that's always true for any new utility model, New utility models, this ambiguity version parameter, and how to calibrate that, how to estimate that. And there's no exception here, We can use data to estimate, by whatever econometric methods, maximum likelihood, or whatever, structural estimation, Bayesian, whatever. So we can estimate this. But here we do calibration, we match data, We can back out a parameter. But you may ask, what is reasonable? And we say, we can do some experimental evidence. So that's the static model in the experimental literature. We can do this too. The one question we may ask, so how much do we want to pay to avoid ambiguity? So something like similar to risk aversion. You have risk premium or certainty equivalent. You have some estimate, and you can think about whether the parameter is reasonable in terms of this kind of thought experiments, or you just do the real experiments. But we can do this similarly. And finally, there's also this detection error probabilities. There's also another way to justify whether the parameter is reasonable. All right, so let me talk about this asset pricing applications here. So we embed this ambiguity model in a representative agent consumption-based model. It's pretty much standard, model here. So this consumption process is regime switching, and the two states. Here, this volatility is constant, all right? But this drift, here the growth rate is a Markov chain of two states. So I assume the state 1 is the high state. That's the boom. 2 is the recession state. Okay, and the dividends, the aggregate dividends, are leveraged claim of consumption. Here is leverage parameter, and this parameter controls the growth rate, and this is the volatility. Okay, and we can compute this posterior, Bayesian posterior, in a standard way. However, in decision making, decision maker does not solve the model using this Bayesian way. You cannot compound these two distributions in the utility function. All right, so this is the utility function here. That's the CS form, and this is risk version gamma. This eta is ambiguity version of. And this if eta is equal to gamma, you can see these two can be reduced. You're going to get the epsilon zero utility with learning. Okay, and you learn this hidden state, so the agent does not observe the regime. We don't know whether it's recession or boom. And then if you take the limit, so that's the multiprice model, the minimum, the two states. Okay. All right, so here is the most important thing for asset pricing, the pricing kernel. We can compute the pricing kernel easily, pretty much in very tractable, intuitive form. You ignore the last term here. That's the epsilon zing utility. The first term is standard power, the power utility, and this is epsilon zing adjustment. You can see here. You need the gamma to bigger than rho. Basically, you prefer the early resolution of uncertainty, and to make this countercyclical. Okay, and here this is the ambiguity adjustment. That's new in our paper here. Okay, and you can see here, this the Z is the state. You have high state, low state. Okay, and typically for the high state, this value is a little bit higher. This weight is higher, but low state is smaller. However, we have ambiguity version. Eta is bigger than gamma, so that means that you put more weight on the recession state, on the bad state. Okay, so that means you have pessimistic behavior. You can generate a countercyclical pricing kernel, and this helps asset pricing. So we're going to show you in a minute. So this actual term helps a lot. Also, I will emphasize here, this is not observation equivalent to recursive utility or epsilon utility. It's not equivalent, also observation equivalent. It's completely this is a new model. Okay, new class of models. And then the asset pricing. So this the standard asset pricing formula. This is always true. It is a pricing kernel. You have any return, any assets. You can get this formula here. And because we have homogeneity, you can solve the price different ratio. Is homogeneous. The only state here is the belief here, posterior belief. All right, and we can compute the stock return is given by this expression. So we want to understand the equity premium. Basically you compute this conditional equity premium. So it depends on the covariance term, the covariance between the pricing kernel and the stock return. So you want to understand why you can generate a higher equity premium. So what's the intuition here? The intuition is that you need this covariance term to be big. How to make this big? So that's the intuition here. In bad times, stock returns are low. But however, your hunger, that's what I learned from the Cochrane book. Your hunger, your marginal utility is high. Marginal utility basically is pricing kernel. This must be high, yeah. Or survey paper I read, yeah. So this covariance must be high, how to make this high? That's basically you need countercyclical behavior, right? There are many ways. Habit formation. That's one way to do this, That's a basic intuition. So that he has this kind of. So why do people fear stocks? That's what they wrote in the paper, Habit Formation, JPE. So here we say, why do people fear stocks? Because they are ambiguity verse. Okay, that's one answer to this. It's not a habit, it's ambiguity verse, because we can generate additional countercyclical behavior, and there can high negative correlation here. Okay, and then so we relate to the variance premium. We want to understand what generates variance premium for this model. So that's the expression for variance premium here. Okay. So this is the risk neutral measure. This is expected variance conditional stock variance. And this is the physical, under physical measure, expected variance. Okay, the difference is the variance premium. So we want to understand why, how to generate a high variance premium. Okay, and we do some algebra. We can decompose this term, this variance premium into three components. The first component is mu t minus mu t hat. Mu t is the belief, is the Bayesian belief about the high state. Okay, and mu t hat is the ambiguity adjusted beliefs. Okay, so we have the expression here. This ambiguity adjusted, this is the pricing kernel. This is ambiguity, adjustment here. And ambiguity adjustment, basically ambiguity versus adjustment put more weight on the recession, on the bad states, and lower weight on the good states. And you make this lower, make the belief lower. And the pessimistic make the bad states more likely, the good states less likely. Okay, so basically the difference will be higher on the ambiguity version. So that's the key intuition here. All right. And here, this standard, this, in the bad state, the 2 is the bad state. The variance is higher. So this is positive here, okay? But this is important here. That's depend on your belief, And that is the whole, the whole story about ambiguity version. You are pessimistic, You put more weight on the bad states, recession states. And this helps. This generates a higher variance premium, okay? And similarly, the last term, this last component, this covariance component, and here it is weighted by the 2 states, the probabilities, the beliefs. And by the similar intuition I already explained, you have more weight on the bad states. And this can generate a higher variance premium, okay? So that's the basic intuition here. And then we do some quantitative work, okay? So not much theory paper, so that's why I think it is, but I hope it is intuitive here. Is compared to Drexler paper, he's much more complicated model, but our paper was rejected in JF, But anyway, he did the first time, It's intuitive, but it's simple model, yeah.
So the model, how is it different from your model with the Jew?
Different from which?
Your paper with the Jew?
Yeah, so it's the same model.
It's the same model, but just pricing different.
Yeah, you apply to variance premium, yeah. So, but that's also people roughly complain about, But I think we don't propose a new model. Yeah, we want to explain something, We use a model to explain something. I would say this, It's not a theoretical contribution much, But we have this, I think this nice decomposition. I hope people can value this, And also, we explain something. So, all right. It's not a theory paper. All right, so we use Shiller's data, this annual data, century-long data. And this, the high state is persistent, very persistent, the bad state is very bad, It's like a disaster, but not, Yeah, not very long, And this is the leverage parameter, about 3, And this growth rate, we want to match the dividend. We assume dividend growth rate is equal to the consumption growth rate. Dividend is more volatile, so we can back out this parameter. And we also assume the EAS is 1.5. That's the literature in the Epstein-Zing models, And we also assume the risk aversion is low. So, we suppose risk aversion is low. So how much ambiguity aversion can you explain? We want to focus on ambiguity aversion. And then we calibrate the 2 parameters, this beta, this discount factor, and ambiguity aversion parameter. Okay, so here is the prediction of the model. So you can see here, this the risk-free rate is the volatility of risk-free rate is equity premium volatility. Okay, and that's the data. And we have several comparison models. Model 1A, that's the standard CRA utility with full information. And then we also study, this with learning, with CRA utility. And this Epstein-Zing utility with full information. And this Epstein-Zing utility with learning, okay? And the last one, that's the all model with ambiguity aversion and also learning, okay? So we have the comparison here. And you can see our model, we can match this, that's how we pick parameter. And this volatility is low, risk-free rate, okay? And we can match this volatility of equity premium. It's pretty reasonable. In the data is about 18%, 19%. Okay, so this is variance premium here. The data is this, and this is the data reported by Drexler. But my co-author has different, but my co-author is pretty confident that he's right data. But it's very close here. But the volatility is pretty far off, but this data, okay? In terms of prediction here, this is our prediction here. So the variance premium is pretty close to the data. The volatility is also pretty close to the data. This is the data reported by Drexler, but our model is higher. The data is higher. And this is the autocorrelation of variance premium, I'm sorry?
So when you define the variance premium in the model?
Say it again?
When you define the variance premium in the model, presumably you need some conditional expectation of the of the variance?
Yeah.
So that's then based on the models.
So the first, this the data, yeah. So this is the model, yeah. This we computed from the model. We do simulation, you know.
So I would expect that because it's about the conditional expectation of the variance, you could sort of, the conditional variables that you have in your model might generate a different conditional expectation than whatever guy.
Yeah, so I will show you. Yeah, so let me show you this. The model is over there. Okay, so let me show you this. What's going on here? So this is the components we did decomposition and see. Oh, so time is too fast. I thought I have 20 pages. Only 20 pages slides, not too long. You know, time is too fast. You know. Okay, here it is 3 components. We see how our model can generate a high variance premium. You can see here the first component is the belief difference, right? The distorted belief, you know, that's why our model is 10 times, you know, more than about 10 times higher than the other models, okay? And the second factor is also much higher than that. So that's how we generate. We did some decomposition, you know. We see what generates the high variance premium. And then let me show you some figures here. So why our model has, you know, can help, you know. So we did the decomposition for these 3 components. So this is the conditional variance premium given all the states. You know, it's a function of the states. You know, this is the posterior beliefs, and that's the belief difference. You know, you can see with the ambiguity version you can amplify. You know, okay, and similarly to amplify this variance difference. Okay, and this is the last component. All right, this with the ambiguity version you have big amplification effects. All right, so I can skip this. You know. And this is the conditional variance. I think this is Martin asked this. You know, this conditional variance. You know, so our model can amplify this conditional variance. Okay, and this is the historical data. This is consumption growth data, and then we can compute this posterior Bayesian beliefs, and then we can do this historical. That's what Mukherjee did. You know, this historical model implied variance premium. Okay, we feed it into the data and compute. It's not simulated. It's computed from the model, you know. And this variance premium. It's very volatile. And also we compare with data. So let me skip this slide. So we still have some limitation. I would acknowledge this, you know. The data is only available starting from 1990, you know. And our model can capture, this somehow, this.
Like daily observations and yearly ones.
Yeah, that's good. Yeah. So here, this is the daily. This is the annual data. Yeah. We saw models on annual. So this. So I'm sorry. So I have a data co-author. So he's not here today. Sorry. So but anyway, our model has trouble to explain 1990s. I already mentioned what's going on there. The reason is that the 1997, that's the financial crisis. Asian financial crisis, okay, and the U.S. did not have recession, okay, so we have trouble to explain this part, but we can capture this recent recession, also this recession here, So, and that's the last slide. I'm done, Yeah, this is conclude. The paper provides an ambiguity-based interpretation of variance premium, and so we have this decomposition result. Variance premium is a compounding effect of the belief distortion regarding the 2 states, and also the market variance differentials. And then, we show that the calibrated model with ambiguity version can generate a mean variance premium, reasonably well. The model can endogenously generate time-varying stock market variance, the volatility, and also time-varying variance premium. Okay, so that's it.